Yeah, so now what we'll do is the following. So what we'll do is the following. Yes, this is precisely what we have to do. Now what we do is the following. Using this theorem, we interpret something. So what we have here, we have x minus x tilde by x by norm A times norm A inverse times norm B minus norm B tilde. So yeah, now okay, so we'll interpret this. See, sometimes it so happen when you're solving a system, so for example you are solving this system Ax equal to B and B is not you perturb B, you take some approximation for B and let it be B nu, some perturbation of B, or maybe some approximation of B, then obviously you will not get x as the so here the x will also change, right? So now what this theorem tells us, that the error, so this is the error, right? So what is the relative error in the solution? So relative error in the solution so relative error in the solution will be x minus x nu norm by norm x, and relative error in the vector the given vector I should write, but okay, that is clear from the picture. It is norm B minus B nu yeah. So this theorem says that you can actually control the relative error in the solution. So you can control relative error in the solution by some constant multiple of relative error in the given vector. Yeah. So note that this quantity plays an important role here. This constant is called the condition number of A. This is called the condition number of A, and it is denoted by kappa A. Okay. This is denoted by kappa A. Yeah. So the condition number of a matrix depends very much on the vector norm. Okay, because see, this norm A is the matrix norm subordinate to a vector norm. So you change the vector norm, the matrix norm subordinate to that vector norm will change, and hence the condition number will also change. So it is clear that, from this, if condition number is small, then the relative error, in the solution will also be small whenever the relative error in the right hand side vector is small. On the other hand, if condition number is very large, then it might so happen that relative error is very large. Okay, so in that sense, condition number measure the change in the solution when you change your right hand side vector. Okay, so we will consider this one example. We will consider this with one example. The linear system (5x1 plus 7x2) equal to 0.7, then 7x1 plus 10x2 is 1, and if you solve this system, I am giving you the solution. It has the solution or maybe let us first convert it in the Ax equal to b framework. 5, 7, 7, 10. And here you will have x1, x2, and 0.7 and 1. Yeah, so this is Ax equal to b, this system, and this determinant of A is 50 minus 49, which is 1. So A is invertible. We have proved earlier that if A is an invertible matrix, this happens if and only if determinant is non-zero. So let's say, and this system has the solution of this system will be unique, and it has the solution x1, x2 is 0, 0.1. You just plug these values in the above equation and you will see that this value will give you the right hand side. Yes. So let this solution be x. Okay. Let this solution be x. Now if you perturb the system, like perturbed system, so for example, now A you are not changing obviously. Some vector here. You change 0.7 by 0.69 for example, and 1 by 1.01. And now you want to solve this system. So again you will see that, okay, let me just not write this. Yeah. So now if you want to solve this system, I'm giving you the solution already. So it has the solution has the solution, new solution, let's say x tilde to be minus 0.17 and 0.22. Okay, and this is your b tilde. This right hand side vector is your b tilde. Now if you compute the relative error, if you compute this quantity, we want to compute the condition number. Okay, so first let us yeah, so in this case what we do, the easiest is to calculate is the supremum, matrix norm subordinate to the supremum. So let us compute that. So what is A? Is 5, 7, 7, 10, and A inverse will be, determinant is 1, so 1 upon determinant A is 1, so it is just 10, 7, minus 7, minus 7, right? Now what is this norm? Remember, this is the column sum. Okay, so this norm will be 7, and again this will be same as this. So hence the condition number is, I think, 17 square, which is, so what is 17 square? Okay, I think it is 289. Yes, 289. So the condition number is very large. Okay, so the condition number is very large. So we should expect a great relative error. Okay, so let us compute. Okay, in this example we can see actually what is the relative error. So norm of x minus x tilde we compute, because this is precisely the relative error in the solution. Okay, now what is x minus x tilde? It is, if you compute, okay, I will not compute, I have computed already, so it will turn out to be 1.7, and the third quantity, this is the relative error. This is the relative error in the right hand side vector, right? The relative error in right hand side vector, and if you compute it, it will be 0.01. So let us predict what is happening here, because the part of the numerical analysis is to learn how to predict the data. So what is happening here is the following. See, you perturbed this b tilde, right? You had some b 0.7 comma 1, and you changed this b to 0.69 and 1.01. So the relative error, it turns out to be 0.01, which is significantly very small. Okay, But even with that significant change, even with that small change in the right hand side vector, the relative error in the solution is coming out to be 1.7, which is huge, okay. So as expected, we should have a high condition number, and in this case we see precisely the condition number is 289, okay. So this condition number is the condition number in this sense measures the change in the solution of the system when you change your right hand side vector, okay. Now there are some terms, okay, so there are, okay, let me just write them as remark. So a matrix with high condition number is called ill conditioned. A matrix with large condition number is called ill conditioned. And a matrix with a small condition number is said to be well conditioned, okay. So let me write what I have been saying since we have defined this notion of condition number. So a condition number measures a change measures relative measures a change in the solution when the right hand side vector is changed. Right hand side vector is changed or perturbed, okay. So higher the condition number is, greater the relative error in the solution. So that is why keeping the condition number, having a matrix with condition number small is really important, okay, is really important. Yes.